example I want to do in these lectures is one where we have minus signs showing up. So the problem is something like this. So we have a limit of a function, but instead of everything being plus, we've got some minus signs. Now we still know that as n gets really, really big, the denominator of this fraction should go to 0. So we expect the limit to be 0, but we're going to see some problems are going to come up. So again, let's set up our template. So as always, we have let epsilon be greater than 0. We have our setup with n, and we don't know yet how big it needs to be, but our intuition is that if n is big enough, then the distance between an and our limit should be very, very small. Right? So here our limit was 0, and so when we subtract that from the formula, we're just left with that quantity. And now, a very first question we have is, what do we do with those absolute value signs? Can we just get rid of them? Well, we actually can't, because the problem is this quantity down here could be negative. And if it were negative, then when we remove the absolute value signs, we'd have to put a minus sign in front of it, right? So the problem is that this might not be equal to its own absolute value because it could be negative. In fact, if n equals 1, then we'd get 1 minus 50 plus 2 minus 7. That would definitely be negative. And so we can't just remove the absolute value signs. However, if n was reasonably big, for instance, if n were bigger than 50, then the quantity on the bottom will be positive. And so why is that true? Well, here what do we have? We have n cubed minus 50n squared. So if n is bigger than 50, then n cubed is going to be more than 50 times n squared. Right? We can just literally multiply this n greater than 50 by n squared if we wanted, or we could just appeal to our intuition. So now we've got something that's positive, because this is going to be more than 50 times n squared. And then what are we adding to it? We're adding 2n minus 7. Well, again, if n is bigger than 50, then 2n minus 7 is going to be at least 50. So what this means is that if we go to the next slide, I hope you can see the color on this. I've got this n greater than 50 in red, and if that's true, then what we're going to have here is that we have an equal that we'll have an equal sign, right? So as long as our n is at least 50, we'll be able to simplify this one more step. And you see how I've kept some question marks here because we might have more, right? We might need to put more stuff in the Archimedean property. And our idea is that, well, we don't care how big n has to be. N can be as big as it needs to be. And in particular, if it needs to be bigger than 50, we can guarantee that. So let's keep going. So what we want to do is now we want to look at this and we want to say, well, can I simplify it at all? Well, a bunch of stuff just popped up, so let me talk through that. So the first thing we do is, and these proofs are complicated. I'm acknowledging this is one of the hardest proofs we've ever seen, but I want to talk you through it step by step, and on Monday in class we're going to do one like this as well. But the idea is, well, let's just factor out an n cubed. Right? So we factor out an n cubed, and what's left on the inside is 1 minus 50 over n plus 2 over n squared minus 7 over n cubed. You should just double check now that you can see sort of how we got between those two. And then my idea, which is a really kind of the big idea in this slide, is that, well, look at what we're doing. We're taking 1 and we're subtracting something, and then we're adding something and we're subtracting something. But my intuition is if that number n is huge, like say it's like 1,000,000, then I'm subtracting something so small and adding something and subtracting something even smaller that what I'm going to get is I'm going to get 1 minus something. It's probably going to be like 0.99, right? And so if we have a 0.99 in the denominator, then that's going to mean we have a smaller overall fraction than just having a 0.5 in the denominator, right? So we can't appeal to intuition completely, so let's try to make this a little bit more rigorous. So if let's see how big it would have to be. Well, let's see, if n were equal to 100 or more, then what would happen is I'd do 1 minus 50 over n. Oh, that would be exactly 1/2, because we'd subtract 50 over 100. And then we'd be adding something. Okay, that would be bigger. And then we'd be subtracting something. Oh, but that's got to be really small, because like n cubed is so much smaller than n squared. So that seems like n at least 100 should work. So let's just try it. So I've written down the steps. So if n is at least 100, then the blue quantity will be bigger than 1 minus 50 over 100. Right, because if n is bigger than 100, then we are going to be subtracting a smaller and smaller fraction. And so I've just done that. And now what I can do if I really want to, so I've simplified the 50 over 100 to 1/2. And then I've pulled a 1 over n squared out of the last two terms. And I see I get 2 minus 7 over n. And of course, if n is bigger than 100, then 2 minus 7 over anything bigger than 100 is going to be positive. And so at the end of the day, we get 1/2 plus a positive number. So this quantity in blue is going to be a bigger number than 1/2, which means that it contributes to a smaller fraction. So unfortunately, in analysis, a lot of writing proofs is figuring out exactly how to do statements like this and understanding exactly why they're true. And a lot of times writing more steps or more explanations doesn't make it any clearer. So at some point we just have to think, and this is where our brains kind of go into overdrive, we just have to sort of think, man, why is this going to be positive if n is at least 50, and why is this going to be at least 1/2 when n is at least 100, and if this is bigger than 1/2, why does this make this smaller than 1 over 1/2? These are questions that are just worth spending a lot of time. So I would expect, even if you have to freeze this slide or re-listen to it many times, and then eventually maybe come talk in office hours, this is how the ideas are going to sink in. I realize this is a tough problem. I would say low likelihood I would give you something like this on the first midterm. Definitely on the second midterm, though, once we've got more experience. Anyways, let's continue. So we've seen that if n is at least 100, then we can go one more step. We can put this inequality in. And so I've done this. I've put the 100 in blue, and I've got this inequality here in blue. And now we're sort of home free, because now we can just simplify the fraction. We can do some stuff we're used to. 2 over n cubed is less than or equal to 2 over n. Since n is greater than or equal to capital N, we can compare these two. And then at the very end, I've got a less than or equal epsilon. That should just be a strictly less than epsilon. But at the end, well, we still need it less than epsilon. So what are we going to need for that to be true? Well, that's something we're used to, right? For that to be true, as long as n, capital N, is bigger than 2 over epsilon, which I've now put up here, that's going to be true. So let me just finish the slide. So there's a ton of stuff going on here, which is really kind of cool. So we've got the red 50. So as long as we pick n bigger than 50, this is going to be true. As long as we pick n bigger than 100, this is going to be true. As long as we take little n bigger than capital N, this inequality is going to be true. And as long as we take capital N bigger than 2 over epsilon, this inequality down here, which again, I should have written a strict inequality. Honestly, it's fine if you just do less than or equal. It's equivalent. So we're in perfect shape. So now that we have all the colors here, I hope you can see sort of how all the steps came together in actually kind of an interesting way. But this proof is hard. And we probably don't want to do 5 homework problems and come up with this argument 5 different times, which is why in analysis class what we're going to do is prove one theorem that sort of does this in general. And so in class, I think on either Wednesday or the Monday after that, we will get to a problem where we will basically prove that any polynomial, if you take the limit of 1 over it, as long as the degree is at least 1, then that limit's going to go to 0. So that's something I'm looking forward to. So that's it. Thanks.